In this lecture, I'm going to talk about how you actually obtain properties of periodic structures from your quantum mechanical calculations. Some part of this will actually be used in your lab too, so I will give you a hint later. So this is what a typical calculation looks like, right? And it's very similar to your lab number 1 and molecular calculations, okay? You usually start with some input structure, usually comes from experiments. You then do geometry relaxation. In other words, you get the lowest energies configuration of your atoms, okay? And then you follow that by either static energy calculations or some other calculations of the property that you are interested in, okay? Now, in lab number 2, you are not actually going to do geometry relaxation at all, right? The reason is because we want you to just do static energy calculations to actually get the potential energy surface of your crystal structure, right? So geometry optimization is also known as relaxing the crystal structure. So it just simply means that I'm going to keep modifying my lattice parameters and the position of my atoms until I basically get the lowest energy structure within that local space that I'm sampling, okay? Now, but even in geometry optimization, unlike in the molecule case, there are actually more options when we are talking about periodic structures, right? So there are a few options for geometry optimization. The most common one is what is called full geometry optimization. In other words, I'm going to allow everything to change. I will allow my cell shape, cell size, and the position of my atoms to be modified during the relaxation process to find the lowest energy structure. Now, there is also the fixed cell shape and size type of geometry optimization. This is what this simply means is that I am not going to allow my lattice parameters to change, neither nor the shape of it, right? All that I'm allowing to change is just the positions of my atoms within that unit cell, okay? Now, this is typically used when you are modeling certain type of systems where you essentially already have a lattice parameter that you believe is correct. Now, the classic example is, for example, in defect calculations, right? So very frequently, because you want to model the effect of an isolated defect in a big cell, you will actually fix the cell shape and size, and then just allow the atoms to relax, okay? There's also what is called constrained geometry optimization. So this is even more, you're adding even more constraints to the cell shape and size. In this case, what you're doing is that you are essentially saying, I have, say, 20 atoms, I'm only going to allow 10 of them to relax and the other 10 will stay where they are. The coordinates are not allowed to change, okay? Now, again, this is typically a trick used to minimize the cost of the calculations, right? Because if I don't have to consider a certain subset of atoms in my geometry optimization, the space that I have to explore is much smaller. Now, this is, for example, one classic example, when we will come to that later in the course, is surface calculations, right? So when we are creating a surface, typically we only care about relaxation of atoms close to the surface, while the atoms which are in the middle of your slab, typically they are going to remain in a somewhat bulk-like configuration, and we are not going to care about them, all right? And other than these three, which are the most common, there are of course many other combinations, and these three are usually supported in any quantum chemistry electron structure code that you use. Then there are also some other options which may depend on what code you are using, okay? Now, in your lab number 2, what you will be doing is this manual geometry optimization, okay? The way that you do a manual geometry optimization, especially for something like silicon, where you have just one lattice parameter to change, okay? You don't actually allow, the atoms won't change from the default positions, is you plot the energy as a function of the A lattice parameter. Okay, so what you do is that you change the A lattice parameter according to some grid, and you calculate the energy of each point. You do a single point energy calculation at this point, and then you can fit this equation of state for energy versus lattice parameter or equivalently volume to it, and the minimum energy point will give you the equilibrium lattice parameter or equilibrium volume. Okay, so the example I show here is for copper. The one that you are going to do is silicon, but the concept is basically the same, right? So this is something that you will be doing immediately in your lab number 2. Now, whenever we are trying to find the, when we do automatic geometry optimization, one of the things that we always are trying to do is to find the minimum of some function, right? Or it can be the minimum, typically it's the minimum of the energy. So how do we go about finding the local minimum, right? So there's a few ways. So one classic way is basically to use Newton's method for finding an isolated real root. In other words, let's say our initial guess is over here. What I'm going to do is that I'm going to calculate the gradient at this point. I'm going to fit this linear line, and then the intersection with this 0 line gives me my new guess, and then I'm going to redo my calculation, and then I will just keep doing this until I basically get to my minimum point. Okay. Now in n-dimensional, this is the example in just a one-dimensional coordinate. In n dimensions, you basically have this expression over here, right? Now, while Newton's method is conceptually very simple, and you can actually code it yourself in MATLAB quite easily. I actually did that when I was a master's student. Okay. But for very high dimensions, which is basically what we are concerned with, because if you think about it, let's say I have just 4 atoms, and the 4 atoms have 3 coordinates each. That's already 12 coordinates. I have 6 lattice parameter. That's 18 coordinates, right? So I'm actually navigating in 18 coordinate space, assuming no symmetry constraints. And I'm trying to find the minimum of that function of that 18 coordinates, right? So Newton's method is impractical for that kind of problem. Okay, for high dimensions, it's just not easy to do. So people have adapted Newton's method into something called the quasi-Newton method, and I'm not going to go into the details of the method, but basically this is just an adaptation of Newton's method for high-dimensional space. Now, more commonly, another common optimization method used is what is called the conjugate gradient method. So in the conjugate gradient method, rather than just going following the curve this way, basically what you will do is that you will actually go by the direction perpendicular to the direction of steepest descent. Okay, so basically starting from this gas, you will just go down the steepest descent to this point, and then you just keep doing this until you basically hit the minimum point, which is over here. Okay, now both these are typical options that you can choose in your optimization methods. I would say that conjugate gradient is typically more commonly used when you know that your coordinates are a bit far from the equilibrium coordinates. Okay, so in other words, you have reason to believe that your initial guess of your atomic positions is not that great. Okay, then the conjugate gradient method can be more efficient. However, if you are already quite close to the minimum point, then typically the quasi-Newton method is a bit more stable and is also more also quicker. Okay. So yeah, as I said, typically the conjugate gradient works better for difficult relaxations, and quasi-Newton methods works better if you are already near your minimum point, right? This is not something that you actually have to worry about too much in your lab number 2, because like I said, in your lab number 2, you are not automatically finding the minimum, but rather you are actually plotting the full energy versus volume curve. Okay. Now, when you actually do a manual the energy versus lattice parameter or volume curve, you basically get this this potential energy surface of your system. Now, if you are able to do this for multiple different types of crystal structures for a compound, you can basically calculate the phase diagram of your system, right? So, as I mentioned during the lecture on the LDA approximation, this is one of the early success stories of density functional theory, okay? So this is actually the phase diagram of silicon. This is precisely what you are going to do for your lab number 2, except you are not going to explore things like beta-tin structure or hexagonal diamond structure, right? You are actually only just going to work with the diamond structure itself. Now, so in this work, basically what they did was that they calculate the E versus V curve, energy versus volume curve for different forms of diamond, different forms of silicon, and by doing so, you can actually then determine that, for example, the ground state of silicon is the diamond structure, right? This is the lowest energy structure right here, right? And that's the diamond structure, and that's expected, right? We know that most of the silicon that we see out there, they are all in the diamond structure form, right? Now, when you actually compress silicon and you put it under high pressure, you can get what is called the beta-tin structure, right? So you can actually determine what is from density functional theory calculations, you can actually determine what is the pressure required to bring about this transformation, right? So between the curve of the beta-tin structure and the diamond structure, you actually have this common tangent, right? You can draw this line that is a tangent to both this beta-tin and this diamond. And the slope of this energy versus volume graph at this common tangent is basically the pressure, right? And what this simply means is that at a pressure that is given by the slope of this common tangent, my most stable structure is no longer going to be my diamond structure, but rather my beta-tin structure, okay? So that slope actually gives you your transition pressure, right? Now, people actually have studied this for a very large number of crystal structures, okay? So other than silicon itself, people have done this for things like tin, silicon carbide, a variety of oxides, nitrides, and basically a lot of binary compounds, and most of these are semiconductors that a lot of people are interested in. And you can see that basically on the x-axis is the experimental transition pressure for all these structures, and on the y-axis is basically the theoretically calculated LDA transition pressure. And you can see that the agreement is actually not bad, right? So you at least get a fairly good qualitative trend of your transition pressure compared to the one that you get from experiments, right? So yeah. Now, one of the other things that you have to be aware of when you actually do calculations, especially of structures that actually have magnetism in them, is really what's the magnetic ordering of your crystal, right? So for something like copper, because copper is a D10 system, there's no magnetism, so you don't care. But for something like, say, iron, which is going to be the subject of your lab number 3, magnetism is actually important because we all know iron is magnetic, right? You can make so if you calculate the energy of iron for different crystal different magnetic ordering. So, for example, for the ferromagnetic ordering, in which all the spins point in the same direction, versus an anti-ferromagnetic ordering where you have half the spins in one direction and half of the other spins in the opposite direction, and you can also do what is called no-spin calculation. In other words, you do a non-spin polarized calculation. You can see that the lowest energy structure of iron is basically ferromagnetic, right? And this is in line with what we know, right? So when you take a magnet and you basically go and magnetize your iron itself becomes magnetic, right? And so your spins are in the same direction, right? So this is something that you have to be careful about, especially when you are dealing with magnetic systems, and there are a lot of magnetic ions out there, okay? So classic things are like iron, cobalt, nickel, all these things. If you don't have the right magnetic ordering, your energies and your properties can be significantly different from what they should be, okay? All right, now from our energy versus volume curve, you can also get the sum of the mechanical properties of your periodic solids. Now, in the last part of your lab number 2, this is something that you will be doing, okay? So, the bulk modulus is just equals to the negative volume, partial derivative of your pressure with respect to volume. And since my pressure is the first derivative of my energy with respect to volume, it is just given by volume times the second partial derivative of your energy with respect to volume, okay? So this is an equation that you can obtain directly from your thermodynamic relations, all right? So what this means is that how can I calculate the bulk modulus of my crystal? Basically, the way you do this is that if you take this energy versus volume curve for my diamond, okay, all I need to do is to calculate the curvature of my this E versus V curve, and that curvature will already give me this second derivative of my energy with respect to volume, and gives you an estimate of your bulk modulus, okay? Now, so in lab number 2, you are going to do this as the final part of your calculations. From your E versus V curve, I want you to determine what the bulk modulus of silicon is, right? Both in LDA as well as in GGA, okay? Now, what you see here is the plot of the bulk modulus as for different transition metals as a plotted against the experimental bulk modulus, okay? So the crosses are basically the experimental bulk modulus, and the solid dots are the calculated ones, okay? And what you see is that for quite a good number of systems, you actually get fairly good bulk modulus predictions, but you do get some errors for some of these ions in between, right? And some of this is really because, potentially is because maybe the magnetism was not handled correctly, but by and large, this is basically how you can see that the agreement is reasonably good, right? Now, you can also calculate things like the elastic tensor of the every single crystals from your calculations. If you take the partial derivative of your energy with respect to different strains, so the way that you do this calculation is that you apply different strains in different directions to your crystal, and then you calculate the energies, and then you do this second derivative of your energy with respect to your strains. You basically get your rank 4 tensor, elastic tensor, okay? And nowadays, this is something that we can do quite easily with a lot of the codes out there, and there's actually this very nice work by Martin de Jong, where he basically did calculations of the elastic constant and bulk modulus for about 10,000 crystals in the materials project, and he showed that basically the bulk modulus that is predicted from density functional theory are in general quite good agreement with what you get from your experiments, okay? So this data is actually available in the materials project today. You can actually go in and look at it. So is the bulk modulus for silicon. So when you are doing your calculations, I give you a tip. After you finish your calculation, go in and check the materials project. If your value is very far from that value, re-look at your calculations and re-look at your equations, okay? You are probably doing something wrong, okay? If your value is very far from what they get, all right? All right, other than the energies, the other key output from your quantum mechanics calculations is basically your electronic structure, right? So where are the electrons sitting? Which orbitals are they sitting on? What kind of occupancies they have? So the way that we typically represent the occupancy of electrons is using what's called the density of states. Okay, this basically shows you the energy levels and where all the electrons, the density of the states that are occupied by electrons in this, and the density of the states that are within for each energy. Okay, and what I show here is examples from a calculation that was done quite some time ago in 2004 on this very famous battery material called lithium iron phosphate. And what you see is that one main problem with density functional theory calculations is that if you are not applying a Hubbard U, you tend to significantly underestimate the band gap, right? So both iron phosphate and lithium iron phosphate, they are supposed to be fairly wide band gap insulators, but when you actually do a DFT calculations on the on these two materials, you will find that iron phosphate actually only has a small band gap of 0.5 eV, and lithium iron phosphate has a small band gap of 0.2 eV. Okay, and this is contrary to whatever we know about these two materials, right? You go experimentally, they have very low electronic conductivity, so their band gaps definitely should be much wider. Now, this will also show that if you actually apply a Hubbard U value to your calculations to basically properly localize the electrons in the d orbitals of your iron, you can get the band gaps to be the band gaps are actually much wider, and this is actually more in line with what is experimentally measured. Okay. You can also not just look at the density, you can actually look at the full band structure of your crystal structure. So this is the energy bands that are obtained from DFT calculations of copper. The black dots are basically what is measured from experimental measurements, okay, using angle resolved photoemission. And what you see is that the agreement is extremely good, right? It's actually surprisingly good, right? You basically see the curves going through most of the dots, okay? And the reason is also, of course, very simple, because copper is a metal, and the copper is one of the classic examples where your density functional theory approximations actually should work reasonably well, right? When we think about homogeneous electron gas, metals are the classic examples of electron gas, right? So, calculations of metals tends to work reasonably well as well. Okay. Again, this is silicon. So if you go to the materials project, you actually see the exact same plot. Things like your band gap will be significantly underestimated, but generally the features of the band structure still seems to be reasonably well described. Okay, so in other words, if you are calculating things like the effective mass and the general features of your that it has an indirect band gap, for example, all these features are well reproduced. It's just that the size of the band gap itself is wrong. Okay. Now, there are many, other than applying a U value, there are also other ways that people solve this problem. One classic way that people solve this problem is using what's called a scissors operator. The scissors operator doesn't mean anything. It's not a quantum mechanical operator. It just means that I'm going to take a scissors, and I'm going to cut the piece of paper across here, and I'm going to just move the band gap up. Okay, so that's what the scissors operator is. Okay.
So why does why does the density functional theory underestimates or overestimates the band structures? Is there a specific reason?
Yeah, so it is related to the fact that in the LDA and GGA approximations, the electrons are overly localized. So that's one reason. But even if you go to exact Kohn-Sham theory, the problem is in the Kohn-Sham construction, you are creating a system of non-interacting electrons. Okay, so and that's also another reason why the bandgap is significantly underestimated. Okay. All right. You can of course do much more sophisticated things, like you can calculate the electronic structure, not just for the bulk, but also things like the surfaces of your systems. This is actually a very nice work done by another professor at nanoengineering, Professor Song Yang, when he was a postdoc, where he did high throughput calculations of band structures for different systems to basically look at topological insulators. Okay. And he identified certain features of the band structure that correlates with the existence of topological behavior. Okay. All right. Now, so far I have talked about properties of infinite solids or perfect solids, right? So in other words, these are very idealized systems models for materials that we work with, right? So for example, in your lab number 2, you are working with silicon, you are assuming this is perfect silicon, right? Every atom is exactly in the position that they are supposed to be. Your lattice is a nice perfect cube, and you repeat that infinitely in 3 dimensions. Now, real world materials are almost never like that, right? So real world materials have defects, they have surfaces, and they have interfaces. Okay, so if you look, for example, even looking at silicon, right? Most of the silicon that you see in your microprocessors, they are not pure silicon. Okay, they are silicon with doping. So in other words, you have additional amounts of other kinds of elements thrown into them, because you need that doping to basically create your N and P type materials for your transistors, right? So almost every single material that you're interested in, they will have defects, right? They have substitutional defects like the dopants that I just talked about. They have interstitial defects where you have additional atoms sitting in between the spaces of atoms. So things like your steel, the steel that you see everywhere, that's basically carbon in iron, and the carbon is just sitting in between the spaces of your carbon atoms. Okay. You have your anti-side defects. Anti-side just means that you have 2 atoms which are swapped in positions. Okay. And obviously, we don't have infinite solids. At some point we are going to have a surface somewhere. Okay. And more importantly, you also have interfaces, right? What this means is that there are only very few applications where people bother to make a nice, perfect single crystal for the material. Okay, in most cases, any material that you work with, they are polycrystals. Polycrystals just means that you have multiple crystals that are coming together, and the intersection between 2 grains is basically what I call grain boundaries. All right. So how do we go about modeling such imperfect materials, right? So almost all the type of structures that we are going to work with, they can be summarized into one very simple concept, which is called the Supercell Method. Okay, so I'm going to give you a classic example of just a single dopant. So let's say I'm interested not in pure copper, but I'm interested in copper, but with some aluminum doped into the structure, right? So how do I go about calculating the property of an aluminum doped copper, right? Now, the way that I will do this is that I'm going to take my unit cell of my FCC copper, all right? I'm going to create a much bigger cell. In other words, I'm going to multiply this cell in different directions by a certain amount, and then I'm going to change one of the atoms to aluminum, right? Now, this basically gives us a simulation of, say, 1% or 2% dope aluminum in copper. All right. Of course, how many percent? You just take 1 aluminum divided by the total number of copper atoms. You know what's the doping percentage. Okay. Now, there are some important considerations. By its very nature, these kind of calculations are going to be much more expensive than your simple calculations, right? When I'm doing a calculation of SEC, perfect SEC cubic copper, if you go to the primitive unit cell of copper, there's only one single atom in the unit cell, right? So in essence, I'm doing a one atom calculation. When I am doing something like this, let's say I'm doing 3 by 3 by 3 in all directions. 3 by 3 by 3 is 27 multiplied by 4 atoms. That's basically the total number of atoms I am calculating in this aluminum and copper example. Okay, so the computational cost, because DFT also scales very poorly with the number of atoms, it limits the cell sizes that you can actually simulate, and hence it also limits the concentrations you can access. Okay. In many cases, when you do defect calculations like this, you also need to do another type of convergence test, which is very frequently you want to know what is the dilute limit, right? In other words, what happens when you have just a tiny little amount of aluminum in copper. Now, you can't do tiny amount of aluminum in copper, but you can try to increase the supercell size until your interactions between your periodic images of your aluminum is minimized, and then you get a converged answer to what's the effect of aluminum and copper. Okay. So this is one of the most common calculations that people do in the literature. Okay. So for instance, people have studied what I call the DX centers in silicon and sulfur dope aluminum gallium arsenide. In other words, they look at what happens when you put in sulfur or silicon defects in this aluminum gallium arsenide structures, and they look at essentially what are the energy changes as well as electronic structure changes as the result of this kind of dopants. Okay. So you can actually look at what are the broken bond configurations within because of all the sulfur and silicon defects, and correlate them to the features that you see in the DOS or band structure of the system. Okay. There is also, people have also studied such structures in lithium-ion battery materials. So for instance, I mentioned lithium iron phosphate in the DOS calculation before. So one of the most interesting things about lithium iron phosphate is that unlike most of the other battery materials that you see out there, lithium iron phosphate is what is called a 1D ionic conductor. So in other words, in lithium iron phosphate, the lithium channels are just single line, almost like a single line of atoms, right? The lithium just moves along these lines. There is actually very little motion across different channels. Okay, because the barrier for lithium motion across channels is very high. Now, what this means is that this kind of 1D channel for lithium diffusion is very prone to defects, right? So you can imagine that if you have if one of your channel has a substitution or anti-side defect that has a much higher barrier for diffusion, what this would do is that you will block out the entire channel. Right, so then the performance of your lithium-ion battery will then be limited. So people have actually the study of defects in this battery material is actually a very active field of study. Okay, so when you actually study defects, you will also commonly see these kind of plots in the literature. Okay, so this is basically a plot of the defect formation energies of different types of defects, right? So when you are actually looking at something a bit more complicated, so for example here we are looking at zinc oxide, right? There are different defects that can form depending on the type of conditions you are in, whether you are in an oxygen-rich environment or you are in an oxygen-poor environment. that can actually affect what kind of defects are formed, right? And the way that you do this is that you calculate the formation energy of different types of defects. The formation energy is basically given by the energy of your defective structure. You subtract out your total energy of your bulk structure, and then you subtract chemical potential related to the atoms that you add or remove from your system, okay? And by doing this, you can basically construct this kind of plots, which basically tells you what is the most stable defect under what kind of conditions. So for instance, you can imagine the formation of oxygen vacancies, right? In an oxygen poor or zinc rich environment, your oxygen formation, vacancy formation would be more preferred, right? However, when you are in an oxygen rich environment, then the formation of oxygen vacancy may be less preferred compared to, say, for example, the formation of a zinc vacancy, okay? So these kind of plots are very, very useful for making that determination. Now, other than just the type of defect, oxygen or zinc, there is also the question of what kind of charge is on the defect, right? So whether you are creating an oxygen neutral vacancy, you are creating an oxygen vacancy with a 2+ charge or oxygen vacancy with a 1+ charge, that depends on not just the chemical potential of your oxygen, but also the Fermi level of your system, which is essentially the chemical potential of your electrons, okay? All right. Now, one of the things about charge defects is that the calculations are actually fairly challenging, because when we talk about charge defects, the electrostatic interactions tend to be very long range and they are very strong, right? So most of the time when people do charge defect calculations, they don't do true conversion with respect to supercell size, because you will have to go to impractically large supercell sizes to make sure that your Coulombic interactions are all filtered out, okay? So people can, one way to do this is, of course, you just vary your supercell size and you just extrapolate it down to infinite supercell sizes. That's also very expensive. The more general approach is that people use relatively small supercell sizes. They are still reasonable size, but they then apply what is called a correction scheme to account for the effect of things like the Coulombic interactions, the alignment of the band structure of the bulk versus the defect supercells, and then they basically get your defect formation energy of your charge defect, okay? Now, there are different kinds of correction schemes, so there's too many for me to go through. You can look at them in the literature. These are just some examples. There's a very popular scheme called the Markov chain correction that you apply to charge defect cells. There's also this scheme associated with Van der Walle and et al., and also this Zunger scheme, which also is another popular scheme, right? So the Markov chain correction is just given by this expression over here, and you can actually look at there's this work that actually compares the different correction schemes for charge defect calculations, okay?
So do you include them during the DFT calculations, or once you have done?
No, you actually do them after. So basically, if you look at this, the energy is still the energy of your charge calculation. So the energy of the bulk is still the same, and what you do is that you calculate the correction scheme after, okay? All right. So this is a more complicated example of the defect diagram that I just showed, okay? So talk about. So this is these are native defects in zirconium oxide and hafnium oxide, and you can see that you can construct this kind of charge defect diagrams. They actually have to split this up into, this is high metal chemical potential, low oxygen chemical potential, intermediate, and low and high chemical potential for the metal, low chemical potential for the metal, and high chemical potential for the oxygen. And then for each of these conditions, they actually then plot the formation energy of different defects, right? So with respect to the Fermi level. So you can look at this. This for I will show you here. This is basically a oxygen interstitial, okay, and this is zirconium vacancy with a 4- charge, okay. And depending on the chemical potential and the Fermi level, you have different defects that are stable. So for instance, when you have low chemical potential, high chemical potential of the metal, the formation of any of your metal vacancies is going to be not very favorable. So you see that all the defects are basically some form of a charged oxygen vacancies, okay? When you actually have low chemical potential of your metal, you can either form an oxygen interstitial, or you can actually form things like vacancies of your metal ion, okay? So this kind of plots are actually quite useful to understand what kind of defects will form under what kind of conditions, right? All right, I'm going, actually I only have 2 slides, so I have enough time. All right, so you can also do things like Polaron calculations. Polarons are just quasi-particles that are formed when you actually have a charge carrier sitting in an ionic crystal, and that charge carrier actually causes your lattice to distort around that ionic crystal. And in order for a polaron to hop, so this is the alternative mechanism to band conduction, you actually have to take the lattice distortion around each of your charged particle and move that lattice distortion as well, right? And using DFT calculations, you can first of all calculate whether the polarons will form. In other words, whether you have a negative formation energy of the polaron. You can also calculate things like the obtain the DOS of the polaron to see whether the polarons tend to be very hybridized. So what we show here is basically that in the related lithium manganese phosphate cathode material, you actually find that the polaron actually has a significant hybridization with the oxygen bond compared to, say, in the iron system where the hybridization is less, right? And the hybridization actually has a consequence for the migration barrier of your polaron, right? So in other words, the stronger the hybridization, we found that basically the higher the barrier for polaron migration, and that also means that the manganese compound is more insulating, okay? All right, there are also other topics that we will cover in subsequent lectures. One is phonons, and we are also going to talk about surfaces and interfaces as an entire lecture, because that's actually particularly important to nanomaterials, and you guys are in the nano engineering department. And your final lab, which is lab 4, will actually be calculations on surfaces, okay? With that, I'm going to stop here. Do you guys have any questions before we stop? And we have lab number 2 next week, okay? If not, thank you.